Good afternoon, ladies and gentlemen, and welcome to my talk on using implicit bridging with domain-specific languages. My name is Campbell McCausland. I'm a lead software engineer with Leonardo MW here in the UK, and I work on aircraft avionic systems. But before I worked for Leonardo, I actually worked for many years for project technology on xtUML, and I'm actually one of the original architects of the Bridgepoint tool. In that role, I did quite a bit of bridging, supporting it in the tool, and also actually helping customers to realise designs that used bridging, and came up with a few interesting insights over the years, which I want to share with you. Without further ado, I'm going to crack straight into it and talk about the agenda that we're going to follow here. It occurred to me that people may not know what implicit bridging is specifically. I think most people who are at an xtUML conference will be familiar with the concept of bridging in general, but what implicit bridging is like in particular. And having covered that, we'll go on and talk about how DSLs can help with that activity. So what is implicit bridging? Well, let's start from the beginning. The definition of a domain, a separate real, hypothetical or abstract world inhabited by a distinct set of objects that behave according to the rules and policies characteristic of the domain. A very simple statement, but I find it really profound. To me, domain separation is the key to model longevity, stability and reuse. And it's what sets xtUML apart from some of the other techniques that are available in the world. But domain separation comes at a price, and that is, quite obviously, that we need to connect the domains together. And we do that on a domain chart by drawing bridges between the various domains in the model. And the traditional way to connect them together is to use callable artifacts, that is synchronous services, bridge calls, call them what you will. But what they all do is to invoke behavior in another domain and often return some value to be used by the client. These artifacts are not strictly part of the subject matter, but it's worth noting that they do constrain how one domain uses another. That actually you're as the designer of a client domain, by providing explicit bridge calls, you're actually specifying how your domain is going to get used. And when a client domain uses a server domain, then there is a small amount of coupling because the client has to use the domain in that particular way, and that does actually reduce the decoupling and the reusability of the domains on both sides of the bridge. I'm not saying that explicit bridging is a bad thing, but I am recognising that you do have this slight coupling. It's impossible to avoid. So if you love explicit bridging, if you think it solves all your problems, then perhaps this presentation isn't for you. But if you recognise, and if you've ever thought, well, maybe it's good, and I like my separated subject matters, as we all do, but recognise that, well, maybe there's a better way of doing it, then listen on, because that's what implicit bridging is all about. So what is it in detail? Well, it was first introduced in an internal project technology paper by Sally Schleyer around September of 1994, and the paper refers to something called a half table. Sally's background was in SQL databases, and using a join table, which is really what a half table is, was a natural thing for her. And what's important about the concept is that you have a half table because one half of the table refers to elements in one domain, and the other half of the table refers to elements in the other domain. And so to illustrate that, I'm going to show a couple of explicit examples. One of them is an air traffic control system, which I believe was used in the original project technology paper. And then I'm going to introduce a serial interface example that we've actually used, we're actually using inside Leonardo. So Air traffic control system. Here we look at two domains. We're looking at an air traffic control domain, which has subject matter classes such as aircraft, with attributes call sign, position, and some referential attributes, and as we'll see, a current state. And then other things are like a human air traffic controller, a runway, an aircraft gate, an airport gate. And our example in this particular case is going to focus on bridging involving the aircraft. In the display domain, we have a completely different set of subject matters, as you'd expect, with separated subject matters. So here we've got icon, which has a colour, we have icon ID, and we have an associated label with that icon, and so on. And you've got maybe the scale of the display showing how many meters per pixel or whatever we've got. So we're going to map together here the icon or the colour of the icon, as we'll see in a minute, and some relationship to the aircraft. So we're going to build that in a half table. So here's the air traffic control example. We've got a requirement here, which is that the aircraft shall be displayed to the controller with a colour indicating the aircraft status. So aircraft that require a bit more attention from the air traffic controller, those that are departing and arriving on final approach, they're going to be shown in amber. And at most other times, the aircraft is going to be shown in green. So there's our amber. But there's one significant difference, which is that when aircraft are handing off between air traffic control zones, we need to make sure that that is a positive handout off from one human controller to the next, and therefore we're going to show the aircraft that are handing off in red. So we could do that with explicit bridging. We could make a call in the state of in the action language for the state, which changes the colours accordingly. But what we're going to do is look at an alternative here, which doesn't involve any explicit bridge calls. And here's what it looks like. So it's here we've got on the left-hand side of the table, we've got the half that refers to the air traffic control domain, and on the right-hand side, we've got the half of the display that refers to the display domain. And first thing to note is that the first element in the row of the half table is a counterpart object relationship. It's a born and die relationship, so we expect our architecture that implements this to detect when an aircraft is created and go and create an associated icon for it and establish a relationship between those two instances for the architecture to use when detecting state changes. And then the rest of the table is specifying the various states that the aircraft is in. So we've got 4 different states there, and those states are the ones that are called out in the requirement. And then on the right hand side of the table, we're mapping to an attribute value to capture the requirements that the icon has a particular colour. I'm not going to go into the bottom 2 there. That's just to illustrate that other mappings are possible. We're going to focus on the aircraft icon mapping in this example. So just take a pause to remind ourselves of the advantages of implicit bridging. It supports invariant models which have improved longevity and have reusability, because we're not coupling that domain to any one particular way of using it. We're focusing on reusing the analysis of the subject matter, not the design aspect of how you get it to do something. And all of that coupling is focused in on the bridge and captured in the half tables. So it helps to identify and formalize the layered concerns. It's important to realize that this is design independent, so you can actually reuse the same set of mappings between lots of different domains in your model. You don't have to just create an aircraft to icon. It's actually a mapping between an OA state and an OA attribute value or enumeration value. That's the mapping. So you can actually reuse it across multiple different domains. And of course, by extension, you can reuse it when you move to your next project because there's absolutely, it's completely generic. You can reuse it. The only bit that couples it to a particular design are the rows in the actual half table. Everything else can be taken and used again in another project. Lots of different mechanisms possible. Mapping between states and attribute values is just one. You can have counterpart events, you can have counterpart relationships. Anything goes, so long as you don't, as we'll see, violate the rules of xtUML. You can do these mappings wholesale. It's important to note that the technique is compatible with explicit bridges. Just because you use implicit bridging doesn't mean that explicit bridging is out the window. They can be combined, and sometimes it's just, using explicit bridges is natural, and for those it's a good fit. Just go ahead and use it. The benefit is that we have runtime support for these half tables. So the code generator reads the half table and knows what to do to insert into the code. We talked about the counterpart object having a relationship, and whenever an aircraft is created, an icon is created for it automatically. And similarly, when the aircraft moves out of the ATC system, that aircraft is recovered from memory, and the icon would be destroyed at the same time. Lots of different ways to use this. So let's move on and look at a different example now. Here's a serial interface, and this one uses, this is from a real world example at Leonardo, where we use a MIL standard 1553 low speed synchronous bus. It's a 1 megahertz Manchester coded biphase signal, which provides simultaneously data and clock between the different parts of the system that it communicates with. It's usually dual redundant, which means that if some part of the system becomes damaged or fails in flight, then a backup can automatically be cut in, and that's usually done at hardware level. So in this particular case, the domains involved are a serial I/O domain with things such as a message, with a field, with a type definition, which includes things like the resolution, the unit of the field, and any offset and so on that it might have. And typically these are supplied by a partner, because very often in our business it's another company that's actually creating one part of the aircraft while we would be doing the radar. And so it's not unusual for us to receive a definition like this in electronic form. And so our problem here is that we want to map that electronic form of the interface onto an OOA based model of that we're going to use to deliver the product. So on the other side of the bridge, in this case, we've got a client domain, which can be any client in theory, which uses that is based on a meta model, an OOA of OOA. So the elements that we're going to be mapping to on this side are OOA concepts like event, operation, event parameter, and so on. So that's the mappings that we're going to be doing in this particular case. So here's an example of what the half table looks like. Just to give you a little bit of background here, elevation and azimuth are values that are used to point at a particular part of the sky when you've got an aircraft referenced search command. So the command here that we're talking about is an instruction to a radar to search a particular area of the sky. So the azimuth value tells you whether you're looking to port or starboard. The elevation value tells you whether you're looking up, down, or straight ahead. The half values in each case, they tell you how big the search area you need it to be. So a very large half value will make it a very wide search if it's an azimuth half, and a very tall search if it's an elevation half value, if it's a large value. So by combining the half value for azimuth and elevation, you actually get a large square, if you like, an imaginary square drawn onto the sky at some angle from the cockpit. And then finally, we've got two other attributes here which are of interest. One of them is min and max, and that's basically constraining that square in the sky to be a volume. So you can imagine that as an imaginary cube in the sky, where the min value is the face of the cube closest to the aircraft, and the max value is the rear face of the cube. And the radar is going to search within that area for various targets. So you can see this mapping here in the half table. On the left hand side is references to all of the elements in the partner supplied what we call an interface control document, and then on the right hand side of the half table are the mappings onto an event which we're going to call ASN AR command, and you can see the various parameters that we're going to populate. And so what we can do here is the code generator, in this case, will actually generate some C++, for example, which will hook itself up to an interrupt, and that interrupt will go off when a message arrives on the 1553 bus, and it will generate C++ code to mask and shift the data out of the arriving buffer and convert it and place it into the appropriate signal parameter. So we can actually get on with the business of modelling what the radar actually needs to do in response to that command, rather than spending a lot of time developing code that does that grunt work of actually lifting the data out of the buffer. So that's what the half table does. And if you look at it, personally, I think that this is actually starting to look a little bit intimidating. This is just half a dozen different fields out of, and take my word for it, there are hundreds and hundreds of fields in one of these interface definitions, and this is it's starting to get just a little bit daunting. So that's a hint as to why everyone perhaps hasn't used implicit bridging in the past. We used it at Spaywar when I was working for Project Technology, and the actual implicit bridging technique itself was very successful, but we all acknowledge that actually managing the half table data was definitely harder. One reason that implicit bridging hasn't taken over the world is because the common taught technique is explicit bridging with calls. That's the one that all the tools support. It's the one that's in all the books. But there are other factors that make implicit mapping more of a challenge. There's the fact that a lot of bridges rely on a relationship between the mappings and the counterpart objects, so that you can disambiguate which objects are the target of a particular mapping. And that can make the half tables difficult to manage. And finally, the one we just met, which is that for larger systems, sometimes you've got an enormous amount of mapping data that has to be created by hand, and putting it into a half table is it's fault. It's easy to create faults because you don't detect that you've got a problem until you actually run the code generation step to try and stitch everything together with generated code. So enter DSL. How does that help? So a domain-specific language can be constructed to make it easy for the human to construct the mappings. And the tools that we use in this technique, in this endeavour, are things like xtext, which is a tool that's based in Eclipse, but actually you can export the output of Eclipse of xtext and deliver it on a web basis or from a command line. There's all sorts of different ways. It's also compatible with VS Code, for example. So you can actually have a choice of different editing environments in which to use it. But the important thing is that it creates a complete editing environment. It's not just the parser. So you've got error message pop-ups, you've got help, you've got code completion, all the things that you are used to using in the context of an IDE. So the generated environment, this parser with its editors, knows about the domains on either side of the bridge, and I'll show you how it knows about those. So the error checking and the code completion actually happens on the fly as you're editing, and can help a human to actually get the mappings correct and give you instant feedback if you've done something incorrect. One final point is that we can also capture traceability. It's not part of the example that we've got today. We haven't really time for that, but you can use the DSL to capture traceability information for things that are satisfied by the bridging itself rather than the domains on either side. So here's an example of the serial interface. At the top we've got imports, and that's what tells the editor what instance populations we're going to map together. And then the rest of the text, where we've got the arrow notation, which is reminiscent of the pointer operator in C, but here it's just really being used to say that a value on one side of the bridge is being mapped onto a value on the other. So those arrow notations construct the half table. Here we've got some scoping, which actually cuts down on the amount of text that actually needs to be written. You don't actually have to have that. It's a nice piece of syntactic sugar. And here is where we specify the rules for when an event will be generated in the client domain, and we also specify what event is to be sent. So let's run a demo and actually look at this in action. So first of all, we'll take a look at the instance population that's been supplied by our partner company. And as we open this up, you will start to get a flavour for just how many fields we're dealing with here. Hundreds and hundreds of fields. And when we get in about 5 layers deep, we will eventually arrive at the data that we're actually interested in. And there it is. That's the same data that we were showing in the half table. So that gives you a flavour of how big these interfaces can be. Now on the right hand side, if we comment out the imports, you can see that we immediately get errors because the editor no longer knows about the instance population it's supposed to be mapping. There's a complementary set of errors which are caused by commenting out the other import. So here's an error popping up. So it puts it in the margin just like any other IDE and tells you what the error is. You've got completion help, so here's what that looks like. Right hand side is a table of possible completions. Left hand side gives you a pop-up help which is driven by data that's been supplied in the electronic definition of the interface from the partner. And here you can see a bit more pop-ups. There's some stuff that tells you how the data is embedded inside the message and what the offsets are and things like that. Bit more completion help. There's an error message. There's the completion help popping up again. And there's even the ability automatically generated to support a folding editor functionality, which we'll see in a minute. So there we go. We folded up a piece of the specification. So that really supports scalability and allows you to create quite large documents. So there it is. That's what it looks like. So moving on. How is it done? How do we tell xtext about the domains that we want to map? And how does xtext create the data sets which will then pass to the code generator to actually implement these bridges? So how do we tell xtext about the domains? Well, our xtext grammar has a section at the top of it where we can specify what meta models we want to work with. So you just say, I want to work with the OA of OA, or I want to work with the message model code that's been supplied by our partner. Also in here, we can specify that xtext is to find a reference to a meta model instance. So in this example, we've got a reference to the message which is specified in the partner supplied electronic data. So that tells xtext to look for the word incoming and then match it to a message that's in the metadata. And that's how xtext is able to highlight the errors because we turned the imports off, if you remember in the demo. It's also possible to instantiate meta model instances, and we do that. We'll see how to do that in one of these slides here. So how does xtext actually create the data sets? We can let xtext define the meta model that we want it to populate, which we use the generate command, or you can do an import of an existing meta model that you've defined exactly for the purpose. And when you do that, you can use the returns clause in xtext to say, I want to return an instance of my meta model. And that's an illustration of that there in the middle bullet. And when you do that, xtext will check that the assignments that you're making in that rule actually correspond to attributes that are defined in the meta model. So xtext itself helps you to get your DSL design correct. Once the data set is instantiated by parsing, so once you parse it, you've actually got a data set ready for the next stage, which is generating code from. Those models can be persisted if you want as XMI standard files, or you can even more slickly, you can just pass the ADL and the transformation system is smart enough to know that it needs to run the parser on it first to get the data that it needs. So finally, having got that data, you just feed that into your favourite code generator. Our favourite one is Epsilon from the University of York. Highly recommended. It does transformations for both model to model and model to text, so you can do code generation with it. Finally, how do we recommend you use implicit bridging? Is it any different from explicit bridging? Yes, some of the rules for using it or the recommendations are different. Use implicit bridging if reuse is a really important thing to you. If you want the models to have a long life, if you want to get reuse, if you want to particularly doing things like inter-product compatibility. If the meta models you're using are stable over a long period of time, it's much easier to connect your products together because you've reused the same meta models across projects. Also, using projects where there's an abundance of subject matter experts. That's certainly a case in certain parts of Leonardo. We've got lots of people that know loads and loads of stuff about how radar works, but they're not the greatest software engineers. And so if you've got a situation like that, by creating a nice user-friendly DSL for capturing knowledge, then you can actually leverage these subject matter experts and get them to contribute to the development in addition to their considerable valuable knowledge. Use it where, like in the serial example, there's a lot of input mappings to be created. Always remember that there's many possible implicit mappings. We've mentioned 2 in this talk, but there's actually a lot more possible ones. So you would select a handful that covers a good proportion of the application needs. I'm suggesting 80%, and then you cover the remaining 20% by falling back to explicit bridging. Nothing wrong with explicit bridging, as I've said before, just not quite as good at maintaining domain decoupling. So when developing new mappings, take care to respect xtUML execution rules, and the best way of doing that is where you've got a bridged value, treat it in the client domain as read-only. Otherwise, well, you can imagine what can happen. Finally, here's the grammar that I promised earlier on. There isn't room within the slides to show the complete grammar, so I've packed in the grammar of the incoming message side, which is everything that we looked at in this talk. And that, I believe, is the complete grammar that you would need to implement it. If there's the desire, we'll have a breakout session afterwards where we actually construct a solution to the aircraft icon mapping. Just wasn't time to cover it within the time available. There's some references here, the original paper and a paper from Stephen about aspect-oriented modelling that refers to implicit bridging, and there's a reference there for the Epsilon development tools that I referred to. And it just remains for me to offer my thanks to Robert Hobson, who's a systems engineer at Leonardo, who helped in the preparation of the original serial interface specification mapping technique, which I've just demonstrated to you. So thank you for your attention. I draw your attention to my email address. I'd be more than happy to answer any questions that you have that come up after the end of the conference. I'm a really enthusiastic proponent of bridging and all things xtUML, so happy to engage with anyone who wants to contact me. Thank you for your time.